Suppose that we were to use this circuit shown here with the switch initially connected to point A to charge the capacitor C from the battery, and then we move the switch to position B and discharge the capacitor through the resistance R. What will happen is the charge stored on the capacitor will decrease with time, and we can show that on this graph. So here we see that the charge on the capacitor falls away with time as shown on this graph. Now we think about, well, what equation actually describes this graph? Where does this come from? Well, if we think about it here, we know that the current that flows in a circuit is equal to the rate of flow of charge. So we could write I equals dq over dt. So the current that flows in the circuit here, as we close this switch and put the switch to position B, discharge the capacitor through the resistance, a current will flow, and the size of that current will equal the rate at which charge is flowing, or the rate at which charge flows off the capacitor. So we can introduce here a minus, just as showing here that the charge is flowing off the capacitor, the charge is decreasing with time on the capacitor. The rate at which that charge falls is actually the current in the circuit at any particular time. What we also know is, of course, that a current in this electrical circuit will be given by V over R. Ohm's law, we know that V equals IR, so I will have to equal V over R. And also we know our definition of capacitance. Capacitance is the charge stored per volt placed across the capacitor. We can combine those two formulas, so rearranging this, V will equal Q over C. If I replace V here with Q over C, what I've got is I equals Q over RC. And we can combine then these two equations into one. Say, look, okay, here, dq over dt will have to equal minus q over rc. Now what we have here is a differential equation, and we can solve that differential equation here by integrating. I'll rearrange this again. And so we've simply rearranged this equation, divided through by q, basically, and multiplied through by dt, and we've come up with this equation here. Now, those of you who've done A-level mathematics will recognise that what we've got here is an equation that we can integrate. So if we integrate this between two limits, so let's integrate it over a time starting at t0 going on to some sort of time t. At t0, the initial charge on the capacitor, we'll call that as q0. Okay, so at time 0, the charge on the capacitor we're going to call as q0. And after a time t, let's imagine we have a charge q on this capacitor. Now if we integrate 1 over q with respect to dq, what we will get, 1 over q integrated gives us natural log of q. Don't forget, we're integrating this between the limits q and q0. And if we integrate minus 1 over rc with respect to dt, what we will get, minus t over rc. And we are integrating that between t and 0. And so if we work that out, what are we going to get here? We're going to get natural log of q minus natural log of q0. On this side, we're going to have minus t over rc, and here, well, t is 0, then we're just minus 0, so we've got nothing there at all. And what we can then do is use our laws of logs. Natural log of q minus natural log of q0 will equal natural log of q over qo equals minus t over rc. And what we can then do, the opposite doing the natural log is to do e to the power. So we can write q over q0 equals e to the power minus t over rc, or, running out of space here, q will equal, should be a q over q0 there, q0 e to the power minus t over rc. And that is the exponential decay equation. Here, the laws of logs, if you've got natural log of a over b, we can rewrite that as natural log of A minus natural log of B. Just as if we've got natural log of AB, that's the same as having natural log of A plus natural log of B. Equally, natural log of A squared can be written as 2 natural log of A. So those are your laws of logs that we do need to be sort of aware of. So what we've got here is our exponential decay equation, which actually describes that graph here. So this value here, RC, is often referred to as the time constant. The time constant is equal to RC. And there we are, that equation describes that graph. So at any time, after any time t, we can work out the charge that remains on our capacitor, provided we know the original charge that was at the beginning of that time period. Okay, so if we know here what the charge Q0 is, what we can do then, after any particular time, we can work out what charge would remain on our capacitor using this formula. Now, we don't actually need to know, of course, how to derive that formula. That's just giving you an idea where it comes from. So if you don't follow the mathematics, don't worry about that too much. All we need to do really in A-level physics is be able to use and to rearrange this formula. So that's what we're going to look at. So here is our formula that describes this graph here. It describes how the charge stored on the capacitor varies with time as the capacitor discharges. Now this equation is an example of what we call an exponential decay equation. Let's write that down. It's an exponential. Now, as I said, we won't be asked to derive this formula, but what we could be asked is what is meant by an exponential decay. Well, an exponential decay could be defined as shown here. So it is when the rate of decrease of a quantity is proportional to the amount of the quantity that remains. So if you remember earlier, to come up with this formula, our starting point really was that I, current in the circuit, is equal to dq over dt. So we can replace I, q over rc, we said, and we have this formula. So in other words, the rate at which the charge on the capacitor decreases is proportional to the amount of charge on the capacitor that remains. The resistance of the discharge circuit and the capacitance, we'll assume, is going to be constant. So the rate at which the charge on a capacitor decreases is actually proportional to the amount of charge that is remaining on our capacitor. And this sort of relationship is what we call an exponential decay. If we solve this equation as we've seen earlier, we'll come up with this exponential decay equation. So it's an exponential decay because the rate at which the charge is dropping is actually proportional to the amount of charge that remains on the capacitor. We've seen exponential decays in other areas of physics. So, for example, in radioactivity, you'll have a formula like this one. Again, you recognize that as an exponential decay. Remember, the activity of a radioactive sample is the decay constant times the number of nuclei. Activity is just the rate at which the number of nuclei decay. Okay, the rate of change of the number of nuclei decaying per second, if you like, that's what the activity is. And we can see here that that rate at which the number of nuclei decay will be proportional to the number of nuclei that remain for a radioactive discharge, and therefore it is an exponential decay, just as we've got here for a capacitor discharge. Now, it isn't just the charge that remains on the capacitor that decays exponentially, of course, because we know from our definition of capacitance, capacitance is charge stored per volt across the capacitor, so Q equals CV. In other words, the charge remaining on the capacitor is proportional to the PD across the capacitor. So I can replace Q here simply with V. And we've got V equals VO e to the power minus T over RC. V0 here is the initial voltage across the capacitor just before we begin to discharge it, and V is the final voltage after time T of the discharge. So again here, second formula, again the PD across the capacitor will decay exponentially, just as the charge stored on the capacitor will decay exponentially. Now, of course, as the charge drops, as discharge continues, the current in the circuit will decrease. Remember, it's the voltage across the capacitor here that's driving the current through this resistor. As the voltage across the capacitor drops, so will the current in our circuit. Basically, V equals IR. The resistance of the circuit isn't changing. So as the PD across this capacitor drops, the current that it drives through the circuit will drop. Well, we've only got half the number of volts across the capacitor driving a current through the resistor. We're only going to have half the current. So for a discharge circuit, the current in the circuit will also decay exponentially. So those three very similar equations here, when we're discharging a capacitor, these three equations here will all apply, and what we'll be able to see, charge, potential difference across the capacitor and the current in the discharging circuit will all decay exponentially according to this equation, and will all give graphs similar to the one that we've seen here. So we can define this term, the time constant, as being equal to resistance times capacitance. Now, that symbol there is the Greek letter tau, which is the symbol we've used for time constant. Okay, so tau there, symbol for the time constant. What is the time constant? Well, let's think about it. When t equals RC, how much charge will remain on our capacitor? Well, put that into this formula. Q will equal QO e to the power minus RC over RC, which obviously they're going to cancel out. We're going to get minus 1. So what we will have is Q equals QO e to the power minus 1. Or the charge remaining on our capacitor will be the original charge divided by E. Now what is E? E is a special number in mathematics, a bit like pi. It's a special number and it has a value of 2.718. So after each time constant, what will happen is the charge that we have on the capacitor at the beginning of that time constant, the Q0, yes, the charge that we have at the beginning of that time constant will have been divided by the constant E by the end of that time. Now E is 2.718. Because E is 2.718, if we do the original charge by 2.718, we'll get about 0.37. 1 over 2.718 is 0.37 of the original charge. So we're going to have about 37% here of our original charge. So after one time constant here, what you will find, if we start off with Q0, we will have Q0 over E, or 37% of the original charge on our capacitor remaining. That's RC. After two time constants, we continued this on. After two time constants, what you would find again, it'll almost be a third, 37% of what you had at the start. So this one here will be QO now over E squared, we divided by E again. So during each time constant, you are dividing the charge at the start of that time constant by the constant E, dividing it by 2.718, you're ending up with about 37% then of your original charge. Okay, well, what about charging capacitors? Well, if we look at this simple charging circuit here, I'm going to charge the capacitor through the resistance R. What will happen is that the biggest charging current we will have will be when we initially connect the power supply, because at that point the capacitor is initially uncharged and there are no volts across the capacitor, and so we've got the full battery voltage across the resistor driving a large current through that resistance. So initially what we will have is a large current in our charging circuit, and then as the capacitor charges, the PD across the capacitor will increase. And remember, components in series, the PD across each component must add together to give the PD of the power supply. So as we have more volts here across the capacitor, we will have fewer volts across the resistor, because the PD across this plus the PD across this has got to add up basically to the EMF of the battery. So what we will see is a falling voltage across the resistor equaling less current going through that resistor. So the current basically will drop away with time. And we will get a graph that looks something like this. You recognise that before. It's exactly the same graph that really we had with capacitor discharge, and in fact the current, or the rate of decrease of current, is given by exactly the same exponential decay equation that we had earlier on. Now, while the current in the circuit will fall, of course, as the capacitor charges, the charge stored on the capacitor will not fall, it will increase. We're charging up the capacitor. So our graph for charge against time will look very different, and in fact it will look something like that. Okay, so the charge is increasing and then eventually leveling off as our capacitor becomes fully charged. At this point here there will become a time at which no more charge will flow on the capacitor. We've reached the full charge that we're going to actually be able to achieve at that battery EMF. No more charge is flowing at that point, and we can write here the equation that describes that is given there. Again, RC, time constant, and then of course, because the charge stored is proportional to the PD across the capacitor, the graph for V, just like for capacitor discharge, the graph for V against T will be the same as the graph for Q against T. And again, the equation that describes that. All of those equations are in your data book. So the equation for current for capacitor charging is exactly the same as it is for capacitor discharging, but the ones for charge and potential difference are different because when we charge a capacitor, the charge on the capacitor and the PD across the capacitor are increasing rather than decreasing. We have already seen that during the discharge of a capacitor, the charge decays exponentially. And what that means is that the rate at which the charge on the capacitor decreases is proportional to the amount of charge that remains on the capacitor. Remember, in an exponential decay, the rate of decrease of a quantity is proportional to the amount of that quantity that remains. So we can see here that as the capacitor discharges, as the charge on the capacitor reduces, the rate at which charge decreases, represented by the gradient of this graph, is decreasing. Now, one thing that we could possibly be asked to do is that we could be given a graph like this one and asked to show that it actually represents an exponential decay. So let's just have a think about that. How might we do that? Given a graph like this, how could we show that the decay was actually exponential? Well, if the decay is exponential, the charge remaining at the end of a particular time interval will always be the same fraction of the charge at the start of that time interval. Let's see that on this graph. So let's pick a time interval which approximately halves the charge on the capacitor. We could choose any time interval we like, but let's choose this one. So what we can see here is that in a time interval t, the charge remaining on the capacitor will fall from Q0, initial charge Q0, to a final charge Q1 at the end of that time interval. Now what we're going to do now is double that time interval. So whatever t was, we're going to have another time interval from 0 seconds to t seconds. We're going to have another time interval now of t seconds. So at the end of 2t seconds, the charge on the capacitor has now fallen to Q2. Now, if this decay is exponential, what must be true is the following. Provided we choose the same time interval, the charge at the end of that time interval divided by the charge at the beginning of that time interval is going to have to give us a constant value if it's an exponential decay, and so these two ratios must be constant. Now I've chosen here a time interval that is approximately half the charge remaining on the capacitor. You don't have to have it so that it halves. It could just be dropping it by a much smaller fraction. It could just be 90% of the charge that it had at the beginning, but as long as you keep the time interval the same, it'll always then be 90% of what it was at the beginning at the end of that time interval. Why is that the case? Well, let's think about it. We know that if the decay is exponential, it is described by the exponential decay equation that we can see here. So the charge at the end of the time interval is equal to the charge at the beginning multiplied by e to the power minus t over rc. R is the resistance of our discharge circuit, and C is the capacitance of our capacitor. And therefore, if we work out Q1 over Q0, what we've got is What we've got is Q1 over Q0, but Q1 of course is just Q0 e to the power minus t over RC. We can cancel the Q0s, and so that ratio is going to come to be e to the power minus t over RC. We can do the same thing for our other ratio. Again, cancel here Q1 in this case. And of course, we're going to get the same value. So provided we've selected the same time interval here in each case, what we're going to get is really a constant value. If we've kept t the same, we haven't changed the resistance or capacitance of our circuit. When we work out the ratio, the start and end of each of these time intervals, we're going to get a constant basically, if it is an exponential decay described by that equation. So that's an easy way. If you're given a graph, if you choose a particular time interval, whatever time interval you like, measure the charge at the beginning and at the end of that time interval, work out the ratio, do that a couple of times, show that you get the same value, you can show that you've got an exponential decay. While we're on the subject of the exponential decay equation that we can see here, we ought to talk about the rearrangement of that and how we can actually replot this graph here in order to get a straight line graph. So one thing we could do is to take logarithms or natural logarithms of both sides of this equation. So let's do that here now. And we arrive here at this formula. Do anything to one side of an equation so long as we do the same thing on the other. And what we can apply now is the law of logs. If you've got natural log of a product of two quantities, that can be rewritten as the sum of the logs of those two quantities. So natural log of AB is the same as natural log of A plus natural log of B. So I can rewrite that natural log of Q. Now these are really opposite operations. If I take natural log of e to the power minus t over RC, I'm just going to get minus t over RC. Now I'm just going to use the same equation but write that out slightly differently. So what I've done on the right hand side here, I've just swapped these terms around, and rather than writing out minus t over RC, I've written that as minus 1 over RC times t. Minus 1 times t of course is minus t. Why have I done that? Well, so I can compare it to the general equation of a straight line graph, y equals mx plus c. Now, if I was to plot natural log of the charge remaining on our capacitor on the y-axis of the graph, the vertical axis, and I was to plot time as the x horizontal variable, then in our equation what multiplies the x variable is going to be the gradient of our graph, and the plus here will be the intercept, the plus c. So that's going to be our intercept, and here this will correspond to the gradient of the graph. Now because the resistance of our discharge circuit and the capacitance of our capacitor are both going to be constant, we're going to have a constant gradient, and therefore we will have a straight line, albeit of a negative gradient, it's a downward sloping line. So we can see that here. So there we are. If we plot the graph there, natural log of Q, charge remaining on the capacitor vertically, time horizontally, we will get a straight line graph. The intercept on the vertical axis will be natural log of the original charge on the capacitor, and the gradient of this graph will equal minus 1 over RC. So if you find the gradient of the graph, that can be used then to determine the time constant, and if you knew the resistance, you could then work out the capacitance, or vice versa. So just be aware, you might get a graph like that one.